Hello everyone, in this lecture we are going to solve problems on Z transform using the properties. First one is multiplication by n, which is given by Z transform of n raised to k into f of n is equal to minus z into d by dz bracket raised to k into f of z, where this f of z is the Z transform of the sequence f of n, and second one is division by n, which is Z transform of f of n upon n is equal to integration from z to infinity z inverse f of z dz. Again, f of z is Z transform of the sequence f of n. So let us go to solve the examples. In this, we are going to find Z transform and its region of convergence for the given sequences. First sequence is f of n is equal to n square into 5 raised to n for n greater equal 0. Here we can treat this f of n as this 5 raised to n is multiplied by power of n, that is n square, which is similar to n raised to k. Hence, we can use here multiplication by n property. So solution. First of all, we will call this 5 raised to n as g of n. Now, using the definition of Z transform, we will try to find out Z transform of the sequence g of n. Hence, Z transform of g of n is equal to summation n from 0 to infinity, as we have been given n greater equal 0. G of n, which is 5 raised to n into z raised to minus n. Put values of n one by one, that will give us 1 plus 5 into z raised to minus 1 plus 5 square into z raised to minus 2 plus so on. So this is first term is corresponding to n equal to 0. Second term is corresponding to n equal to 1. Third term is corresponding to n equal to 2 and so on. We will rewrite the term that will gives us 1 plus 5 upon z plus 5 square upon z square plus so on, which is in geometric progression with common ratio 5 upon z and first term as 1. Hence, infinite sum will be given by 1 upon 1 minus 5z for modulus of common ratio 5 upon z strictly less than 1. Simplify this, we will be getting g of z as z upon z minus 5 for mod z greater than 5, which is the region of convergence, and this one is Z transform of 5 raised to n. Now, we want to obtain Z transform of the given sequence f of n, for which we are going to use multiplication by n property, and which is given as Z transform of n raised to k g of n is equal to minus z into d by dz bracket raised to k of g of z. Therefore, Z transform of the given sequence f of n will be z into n square into 5 raised to n. So here k is equal to 2, which is equal to minus z into d by minus z into d upon dz bracket raised to k, where k is 2. So it is square. G of z is z upon z minus 5. Now we are going to operate this operator one by one on z upon z minus 5. That will gives us minus z into d by dz of minus z into d by dz of z upon z minus 5. As already we have discussed in the theory part that minus z upon d by dz bracket square can't be written directly as z square into d square upon dz square. We have to operate it like this. One by one we have to operate it on z upon z minus 5. Therefore, first of all, we will evaluate derivative of z upon z minus 5 with respect to z. That will give us z minus 5 minus z divided by z minus 5 bracket square. Here we use quotient rule of derivative. Multiply this result by minus z. Simplify the expression. That will give us 5z divided by z minus 5 bracket square. Now again differentiate it using quotient rule of derivative and multiply the result by minus z. That will give us minus z into, use the quotient rule. Simplifying this expression, we will be getting expression as minus z into minus 5z minus 25 divided by z minus 5 whole bracket cube, and therefore z transform of the given sequence is f of z is equal to 5z square plus 25z divided by z minus 5 bracket cube, and the region of convergence is mod z greater than 5. Now we will consider the second example in which general term of the sequence is f of n is equal to 3 raised to n divided by n for n greater than 0. As here 3 raised to n is divided by n, so we can think of using division by n property. So let us see the solution. In the solution, we will call this 3 raised to n as g of n. Using definition of Z transform, we will obtain its Z transform, which is given by Z transform of G of n is equal to summation n from 1 to infinity 3 raised to n Z raised to minus n, because here we have been given that n is strictly greater than 0, isn't it? Because if it is 0, then 3 raised to n upon 0 will be not defined, infinity, and therefore n is strictly greater than 0, because of which our summation starts in the summation n runs from 1 to infinity. Now put the values of n one by one. That will give us 3 into z raised to minus 1, which is the term corresponding to n equal to 1. Then put n equal to 2. That will give us plus 3 square z raised to minus 2 plus so on. Rewrite the terms. That will give us 3 upon z plus 3 square upon z square plus 3 cube upon z cube plus so on, which is in geometric progression with common ratio 3 upon z and first term 3 upon z. Therefore, infinite sum will be first term 3 upon z divided by 1 minus common ratio again 3 upon z, which is true for modulus of common ratio 3 upon z strictly less than 1. Simplify this term, we will be getting it as g of z is equal to 3 upon z minus 3 for mod z greater than 3, which is the z transform of the sequence 3 raised to n. G of n is equal to 3 raised to n. Now we want to obtain z transform of the sequence f of n, for which we will use the property division by n, and that will so we will recall that property, which is Z transform of g of n divided by n is equal to, which is evaluated as integration from z to infinity z inverse into g of z and integrate it with respect to z. Therefore, for the given sequence, it will be z transform of 3 raised to n divided by n is equal to integration from z to infinity z inverse into z transform of 3 raised to n, which is 3 upon z minus 3, and integrate it with respect to z. We can take 3 outside and z inverse can be written as 1 upon z, and therefore our integrand is now 1 upon z into z minus 3. To simplify this integration, we will obtain partial fractions, and they are 1 upon z minus 3 minus 1 upon z. That 3 got cancelled. Okay. So we left with this term only. Now the integration is simple. Therefore, it will be ln z minus 3 minus ln z. Limits are from z to infinity. To simplify this further, We will use the property of logarithm and we rewrite this term as ln z minus 3 upon z. Limits are from z to infinity. Still, it is quite difficult to evaluate the value. For that, we will separate the numerator and this term can be rewritten as ln 1 minus 3 upon z. Limits are from z to infinity. Now put upper limit, that will give us ln 1 minus 3 upon infinity, that is 0. So we left with ln 1 minus ln, if we replace z by z, so it will give us ln 1 minus 3 upon z. Ln 1 is 0 and therefore we left with minus ln 1 minus 3z inverse. And therefore Z transform of the given sequence is Z transform of 3 raised to n upon n is equal to minus ln 1 minus 3z inverse, and the region of convergence is mod z greater than 3. So in this way, using multiplication by n and division by n, we have seen how to obtain Z transform of the given sequence. I hope you have understood this. In the next lecture, we are going to solve problems on next two properties. Thanks for watching this video.